Today, me, Deepak, Kaushal, and the HiMech group would like to present to you the control of humanoid robot using gesture and imitation. This project is basically an extension of teleoperation of a robot from a far distance, also known as remote control, in various situations, like say for example in the hazardous conditions where human cannot go, or in situations where we require more power than the human can give. In such situations, such a project is very useful. General teleoperation robotic controls generally involve buttons or joystick, but in this project we are trying to control a robot using Kinect, and the advantage of this method is that we will be able to interact naturally with the robot. Since the robot is directly imitating the human does not require special knowledge to control the robot. So in this project we are trying to take a step towards natural interaction with the robot through Kinect. So the main components which we will be using to actually communicate with the robot are the Kinect, Arduino, PC, and of course the Bioroid robot. First we look at the aims of the project as we had decided. The aims of the project are, the first aim is precise imitation of the human arms by the robot. We would like the robot to be very useful in situations such as, say for example, surgery. The surgeon is in New York and the patient is in, say, Tokyo. So if we are able to perform very precise hand movement, it would be very useful in such cases. So that is one of the aims of the project. We would like to have precise imitation of the human limbs. Other than that, we would like to imitate normal tasks, just walking, bending, turning, etc., which would be very useful in cases like we have to perform a specific mission. So for example, like picking an object, pressing a button, or kicking a ball, or any other task which we want the robot to do. For such tasks, we require these basic functionalities like walking, bending, turning, etc. So next we will look at each component in this control system we have created. The first is the Bioroid robot. Bioroid is an 18 degree of freedom robot manufactured by the Robotist company. It uses dynamic sill servos as its joints, and its weight is almost 2 kgs, and it has 3 degrees of freedom in the hand and 6 in the leg. And next we will look about the Kinect sensor. Kinect sensor is manufactured by the company Microsoft. It has 3 ways of taking images: depth image, RGB image, and IR image. So using the combination of 3 images, it can detect and calculate the position of any object in 3D space very accurately. So in this project, the main aim basically consists of procuring data from the Kinect, sending it to the robot. In between, we will be doing processing of the data which we get from the Kinect in various ways. Before we get into what processing which takes place, I'd like to tell you about how we actually send the data from Kinect to the robot. So the first step is from Kinect to the PC, that is through the USB cable and 3 software. They are the Simple OpenNI library, the Microsoft Kinect SDK, and the processing IDE. Using these 3 softwares, we can access the data which is recorded by the Kinect and then manipulate and process it as required. Once the data reaches the computer, we again use 3 different software for processing and analyzing the data. The 3 software are processing, Arduino, and MATLAB. In the processing IDE, this is where most of the processing and analysis of the raw data from the Kinect takes place. This is actually a Java-based IDE whose syntax is very similar to C. Most of the calculation which we will be using to control the robot takes place in this. and once the analysis is performed in the processing ID and we get the angles, they are then sent to the Arduino microcontroller, which is programmed using an Arduino ID, which is also pretty common. And the third and the last software which we are using is MATLAB. We have basically used it to test out our algorithms and to test out the to see whether the robot is working as we wish. Once all the processing and the angles are calculated in the laptop, we then send it to the Arduino using a serial port. For serial communication, we created a communication protocol consisting of actually 11 bits. The first bit just signifies the start of the serial communication. The next 2 bits specify the ID of the robot. The next 4 bits after that specify the position to which the specified servo should move, and the last 4 digits represent the speed of the servo. Once the signal is sent to the Arduino then sends it to the robot. The communication from the Arduino to the robot is through a library called Savage Dynamics library. There are actually, as we have seen the last time we discussed about this paper, there were 3 problems with this. The first one was that the half duplex signals in serial communication for the servos and single serial port in the Arduino, and also the final one was and the final one was the tri-state buffer, which was required to bypass the limitations. So the circuit is given like this. This chip is a tri-state buffer. This chip is a tri-state buffer which is used to convert the half duplex configuration of the servos to the full duplex configuration of the Arduino, and the signals are then sent from the Arduino to the robot via this configuration. So this in short is how we procure data from the Kinect and then after processing send it to the robot. Next we will actually see how we actually process the data which we get from the Kinect. The raw data which we get from the Kinect has to be processed to actually get the data of the user who is in front of it, and Kaushal will explain to you how we perform different tasks and how we get information from the raw data and how we process it.
Good evening, sir. So now we will, as the aim of the project suggested, we need to perform various tasks using the robot, and the basic motions which are useful to perform those tasks are imitating the limbs of the human being, walking, turning, bending, and for imitating the leg, it need to balance on one leg. So now we will look at each of the tasks and the algorithms to convert the data from human being to the robot suitable for each task. So first we will look at hand imitation. So as you can see, this is the kinematic chain of the robot right arm, and this is a human right arm. The problem, as we told you in the previous presentation, was from here to here human arm has 4 degrees of freedom, while robot arm has only 3 degrees of freedom. So we cannot directly give the 3 angles to the robot. So we have to do some kind of manipulation. So what we do, we make 3 planes. One is the plane formed by the upper arm and the lower arm, that is this triangle. One is the plane of the torso, and third plane is the plane perpendicular to the torso. If you observe the bioloid carefully, the degree of freedom controls the direction in which these arms, this angle can rotate. Because if we right now this can rotate like this. If we rotate it, the direction of this motion changes. So in human being, we can see an analogy at the elbow. if we are able to rotate it like this, or if we are able to rotate it like this, the normal vector of this plane is in different directions. So to calculate the first angle, we calculate the angle that this normal vector makes with the vertical, and since the human can be at some angle with respect to kinetic, we cannot take absolute vertical. We have to take the normal to the plane that is perpendicular to the torso. So that's how we get the first angle, that is theta 7. And once we get the once we get theta 7, theta 8 and theta 9 are pretty straightforward, because in human being, again, shoulder has 3 degrees of freedom. So if we rotate this arm like this, it is a 3D angle. But we need to take the component which is, we need to consider the rotation which is in the same direction as the elbow rotation, because in bioloid also elbow and shoulder can rotate in same direction. So we calculate the direction between V2 and V3 vectors, V1 and V2 vectors, and take its component along the normal to this plane. So that's how we get the second angle, that is theta 8. And theta 9 we can directly get from this angle, because it is exactly similar to the human being. So in this way we get a closed form solution of all the 3 angles of the bioloid from the human coordinates. So closed form solutions are important because we need to give the data in real time. So that's how we imitate the hand. After that, a very important concept is balancing. The basic concept that we used in balancing was the center of gravity should be above the support polygon. So if the center of gravity is above the support polygon, the robot will not fall. So using this simple concept, we have implemented balancing in 3 types of motion. The first one that is moving the other leg. So while moving the other leg, we have to make sure that whatever be the movement of the 2 arms and the non-supportive leg, the center of gravity should remain in the support polygon. So if we are somehow able to ensure that, the robot will never fall. So we calculate an initial value of center of gravity and give the angle such that center of gravity is above the support polygon, and then from the forward kinematics that we implemented in MATLAB, we calculated the position of the angles at which center of gravity was going out of the support polygon, and for those values we gave different angles to the motor so that center of gravity is brought back. So through this algorithm, the robot remains balanced in all the conditions while balancing on one leg. So and while imitating the leg, we use similar concepts. We again make 3 planes: the torso plane, the plane perpendicular to the torso, and the plane containing the thigh and the lower leg. So in case of leg, human being has same number of degrees of freedom as the robot, from the hip to the ankle. So what we do, we calculate the normal to this plane, we calculate the normal to the torso plane, and we calculate the normal to the plane that is perpendicular to the torso. Now to calculate the first angle, this angle in the bioloid, it will be this angle. So it is basically the angle which the normal to this plane rotates with respect to this normal, and its component, the angle between this hip, the vector joining the hips, and the normal vector to the leg plane, and its component along this direction. So from that we can calculate the first angle, and the second angle in the bioloid is this one. So since the first angle was the component of rotation along this direction, this angle will be the component of this rotation along the forward direction. Yes. that is a vertical motion. And then the third angle, that is this angle of the bioloid. We observe that this third angle is the angle that this leg makes with respect to the vertical line in the plane of this leg. So we take the component of the angle along the normal vector, and the knee angle again we can directly send it to the robot. So this is how we imitate the leg, and from the value of leg we have the forward kinematics equation. We keep checking that whether center of gravity is going out of the permitted area, and if it goes out, then we bring it back giving the certain commands to fix to certain motors. So this is how one leg is imitated while being supported on other leg. Another important motion is turning. So in turning also we use the basic concept of balancing only. We balance we shift the balance of the robot on one leg, suppose right leg, and if we do that, left leg is free. It can move anywhere. So we give the left leg the angle that we want, by which we want to rotate the robot. So this leg rotates. We place it back, and then we shift the balance to this leg. Now this leg is free. We rotate this leg, and then shift the balance to both the legs, and then rotate the torso. So this way robot keeps turning. And the next important motion is walking. In walking also, suppose we start from the right leg, we shift the balance on the left leg and lift the other leg, place it forward, and keep doing this. And the important thing that we need to take care while walking is, since the size of the foot of the bioloid is very big, we should lift it parallel to the ground. Otherwise, unwanted friction may come and it may make the bioloid fall. And the last motion is bending. Bending may be considered as another form of balancing. In balancing, we were balancing the body in the X plane, that is the torso plane. But in case of bending, we have to balance the robot in this Y plane. So we calculate the angle by which human being bends, give the same angle to the robot, and again through the forward kinematics equation we got from the MATLAB, we adjust the motors once the y coordinate of center of gravity exceeds the permitted area. Now we can see the demonstrations.
키넥트가 빛에 민감하기 때문에
여기 맞췄어?
네 여기
여기 맞췄어?
네 그래서
Did you tune down the kinet to our illumination?
Actually, this illumination is sufficient for the kinetic.
Is it?
Yes.
You don't have to change.
No, this is sufficient.
You don't need to calibrate.
No.
Okay. How about if turn off the lights? Is that okay still?
No. Then it will not be able to locate the human being, and no skeleton will be found. And another thing that I want to tell you is once we figure out how to do all these motions, but then we have to make a user interface so that the person who is operating the robot can run it. So for that, what we do, for simply imitating the hands and legs, the human does the same. But in case of motion like walking, it is not possible that the human will keep walking and the robot will also keep walking. We have to give some sort of a gesture. So what we do, we set some ranges. You can imagine two walls in between. The first wall is at a distance of 2500 mm, that is 2.5 meters from the Kinect. Before that wall, Kinect does nothing. It does not process any data. And the second wall is at a distance of 3 meters. So once the human is between those two walls, 2.5 meters and 3 meters, the robot always imitates the human being. And whatever motion human will do, it will repeat it. If we move our hands, it will move. If we move our leg, it will do the same. But once we go behind a 3-meter wall, the robot will stop imitating. Then it can do only two motions, walking and turning. So, and the codes that we have written for walking and turning, they take the input as number of steps for the walking and the number of times the robot should turn. In one turn it rotates about 30 degrees. So then it recognizes the human gesture. Like to turn the robot, human has to move his right leg, like right hand like this. So the processing code counts how many times human has moved his right leg up and down like this. So it turns the robot that many times. And for walking, the human has to put up and down his right leg. So the number of times the human puts his right leg up and down, the same as the number of steps that robot takes. So this is the user interface that we made. So now we can
Among the couple of manipulation of human beings, you are trying to imitate. There's no jumping.
yeah. Actually,
Jumping possible?
then we will need a strong control system, and for that we need feedback. And to get the feedbacks, we need to put some sensors in it, like at least an accelerometer or some force sensor, which we do not have in this bioroid. So jumping may not be possible with this amount of.
Okay.
Also,
All right, show me.
this is the home position.
기록하고 잘 보면 되나?
돼.
Next, we'll connect with it. Okay, again. Now you can see Deepak is in front of the 2.5 meter wall. So how much he dances, robot will not do anything. So move back. Okay, move back. Yes, now he has crossed the 2.5 meter wall. So robot will imitate his movements. Move the hands.
안 보이는데. 수리 쪽에서 찍어야 될 것 같아.
Actually, in opposite direction. This is facing forward and facing that side, so left and right.
Detected.
about the heat use?
Robot cannot move like this because the direction of rotation of this one and this one is different in this.
Actually, it has less number of degrees of freedom, so
Okay, you said human beings, how many degrees of freedom?
Till-
not counting the singular, it has 4.
4. That has the 3. How about the lower?
Lower is something.
6.
Say 6?
Okay. He was moving too much, so too much noise came in the kinetic data.
Actually,
I can go ahead with them. आगे से शुरू करा
so till now it was the hand. I'll try to balance on my legs. 2 point.
Balancing is not working.
Yeah.
By hand.
Should have
It should have breathed first.
according to the code, it should have tilted first and then started copying the motion. But for some reason, it directly started imitating. Actually, another problem with this particular setup is you can see a lot of loose wires and things like that. So sometimes the motors get unresponsive.
Is that right?
Like you can see, for sending it to the home position, it should go to the home position in one command. But sometimes it takes us 3-4 commands. For now it will balance first.
다시 됐다.
Most of the leg movement is also being copied while balancing. You can actually move the hand also. Okay.
Okay.
We'll actually show you turning.
To show that to turn it, he has to cross the 3-meter wall.
So presently I'm between 2.5 and 3 meters. So
Okay.
like while I was stepping back, I lifted my leg. That is actually a command for it to start balancing. So that's why it's balancing. Okay.
Come down.
That's actually a bug we are not able to find out. It is not going down actually once it starts balancing.
don't lift the leg. Okay, cross. Now it will not imitate his hand, it will only detect the gesture. If he moves right hand like this, it will turn to right once. If he does left hand like this, it will turn to left once.
So I'm doing right.
Right.
Similarly, if I do left.
Sometimes it will turn.
Oh, okay. I think I know what the problem is.
No, do it.
Okay. Yeah.
Yes.
So if I can forward now. So now left side. Yeah. Okay. We can try walking.
Straight.
So walking.
Cross.
Ah. Oh.
flow is so specific. Very romantic. It's very good.
Walked before.
Yeah.
We can show you a video also of it walking. He put the leg one time, so in that he walks 3 steps. Right now also it should walk actually, it's the same code, so maybe because of the difference in surface roughness.
How about the illumination?
It's the same because it is receiving the signal to start walking. So it actually there is no effect of
Yes.
illumination in this case.
It is still detecting the 2 tips of the legs, and the algorithm of the code is you have to detect that right leg is above left leg, then we are declaring a flag variable and a count increases, and it directly sends the command to the, according to that communication protocol, it tells it to walk.
I think the problem is the condition of the surface.
Yes,
That's trouble.
the condition, I guess, for what we programmed the robot to walk correctly differs from the present condition. In the lab, I think it is slightly rougher than this, so because of that, there is slipping between the legs, so that is causing it to fall.
Again, it will improve if some feedback is there, like some force sensor at the foot of the leg, then we can actually get how much friction is there, and we can make the walking a function of that friction. That is a limitation.
Good try.
Now, I'm a group will present to you what they have learned. And
I know what you're saying. even you telling a lie, they can understand. So you should put education in English. I think you guys make a grade for them. We give you grade for you. You grade for them.
Okay. Okay. Really?
안 나오는데?
Okay, this is in English.
나나 물론 저거 해도 돼.
네?
You can use English, but if you cannot. 섞어서 하란 말이죠.
아, 섞어서요?
예.
There are 4 HiMac members are with I student. We separated 2 team, and team A is Kashimo is a leader, and Jung Min-jae and Kim Yo-jung are within the members. And team A's aim is learn about mechanics of biology and analyze. And team B, team B's leader is Deepak, and member of HiMac is Suri and Sung. Team B's aim is data transfer from kinetic to biology. And team A's task was learn about forward and inverse kinematics and find the center of gravity of the biology in terms of actuator angles, and finding the intersection of scaled human arm and biology arm workspace. And team B's task was understanding processing IDE, and using it, and using Kinect via simple OpenNI library, and trying out the various functions, and determining limb angles from Kinect data. And so, my presentation about team A's task. And first, we have to find a bioloid's workspace. So the problem was difference between human arm and bioloid arm. So you can see human arm has very many degree of freedom, but bioloid arm has very simple degree of freedom by 3 motors. So how we did is we analyzed the bioloid arm by mathematical method, and our aim is modeling bioloid arm by using method. So we have to determine the end effector point in result. This code is the rotation matrix about XYZ axis and translation matrix. So we did and we put the point of end effect in this system. So we can. So finally, we input the length of robot arm and for the parameter of the model in MATLAB. And finally, we can modeling the robot bioloid arms in MATLAB. So we verify the end effector point in input the motors angle. Motors angles. It's 3 angles in the MATLAB, so we can know about where the end effector point in the system. This was the Team A's test, and Team B's test will presentation.
Team B deal with Kinect processing program Arduino sketch server button. Especially we detect with Kinect and processing. First, we use simple OpenNI library. We can detect join. So this sentence means simple OpenNI scale right hand change the scale left hand. We can detect left hand. Else neck, head, knee, hip, foot. So we can use that, or we can find the angle. We can detect 3 point, hip, knee, foot. So we this sentence means the angle. Sorry, font size is. But this sentence means the angle is 18 and 90. But its error is big because it is not filtering. And calculate vector and use function angle between. We calculate and return the angle between 2 vectors. So we receive array and average calculate. We can filter in that. So this sentence means the angle is 90.